explain to you the why, the how, and the what it is of BRTECH1. So let's start by who are we? This is Bero of Farbrausch. And whenever in this talk I will say we have done, I actually mean he has done, because Bero is the one who has done all the actual work. Whereas I am Urs of Mercury, and I just act as the voice during the presentation here. So if you want to give credit where credit is due, the actual implementation of this engine has been done by Bero. So what are we talking about anyway? I guess everybody of you has heard about Quake 3 Arena or Quake Arena 3, which is a nowadays rather old shooter written by ID Software. And just so to refresh your memory, I can show this video. It is a first-person shooter that basically defined the multiplayer FPS genre and has this very distinctive look that you may or may not remember from when it first came out. It was very spectacular, but it still also was in 1999, so it was 15 years ago, and is not actually something that you would consider state-of-the-art today. But this is what we're talking about. So it was designed by ID Software, first released, I think the first leaked version of it was seen in 1999, and was specifically designed for multiplayer gaming. It allows players whose computers are connected in network to play against each other, which already did exist at the time, but Quake 3 was, had that as its central core and was the first FPS game to propagate that. And it uses an engine called idTech 3, because it's Quake 3, it uses the third technology generation of their engine, whereas the earlier ones were Tech 1 and Tech 2. Okay, so about idTech 3. Back in the time, 1999, you may remember that not everybody had a 3D accelerator in their machine, so it was very uncommon for a game to be released and to require an OpenGL-compliant graphics card in the machine. It does not any longer, as the previous versions of their tech engine, contain any software rendering site, which meant that at that day everybody had to buy a Voodoo card or whatever was fancy in 1999. I guess the first NVIDIA Riva TNT cards came out around that time as well. But as you can imagine, if you were alive and already coding back in the day, that in 1999 graphics cards were not very much like they are today. There was no programmable pipelines. There was basically just a piece of hardware that could do polygons quickly. So there was no such thing as programmable shaders. However, the idTech 3 engine, when you specify what you want to render, you still have something that they call a shader. In modern language, a shader would more be called a material description. You have small pieces of text, of a script, that defines, by the way, this surface needs this texture and that squiggly thing on top of it, using the following operands and using the following sort order. And let's go into a little bit more detail what this means later on. It also was, and this was very strongly marketed to the press, the first gaming engine that introduced spline-based models. So in earlier games, you always just had polygons describing everything, and in idTech 3, you could also describe surfaces as splines, and it was marketed as, this game has perfectly round corners and perfectly round objects. Of course, what actually happened is that the spline description was tessellated and still displayed as polygons, so even though you had rounded corners, it was, of course, done in small steps of polygons. But it was quite remarkable for the time that this was possible with the hardware, and that level design in the game was based very much around round corners instead of corner ones. Then it had, for the first time, animated meshes that, like the earlier versions, already had frame-based linear interpolation of vertices, so you just had animation frames that were linear interpolated, but it also had attachment tags. So it meant that the actors in the game had separate meshes for their head, their torso, their legs, and potentially their gun attached, which meant that these could separately be animated, which leads to these funny Quake mods you may know, where you have the big heads and the tiny heads, and the heads that grow the longer you play without being shot. These separate animations were possible, and also separate models were possible. And then there were features that, since the graphics card at the time were only basically polygon rendering machines, there was no way to program them to have fog on a specific piece of geometry. However, this engine already allowed what they call volumetric fog, mirrors, portals, dynamic shadows, and CPU-side waveform-based vertex distortions. That means something like water waves on surfaces or wobbly walls or these kind of things. Okay, so let's go a bit into the detail what this shader system of idTech 3 describes. The world is described and rendered as several layers. You have basically, for example, for a solid wall, you have a texture that describes the wall itself, and then you can have different things laid over it, like decals or, I don't know, a plasma surface or these kind of things, and especially environment mapping. Each shader has a sort key. This is important later on, and how the order of these things are being drawn. And they can also have additional surface properties. There's things like roughness to add a little bit of wiggliness on top. And there's also, you can also tag surfaces with physical behavior. For example, you can tag the floor as being slippery or not so slippery. So it does not only store information relevant to rendering, but can also contain game relevant data. Here's one example of this. So this is a Gothic wall street bricks 10. Just, I mean, imagine the side walls in this room would probably look a little bit like that, maybe a little bit larger bricks, but you've got a material that is defined by, so you say what light map you want to use, just this normal one in the level. You can give to the texture coordinates a turbidity, basically a sinus displacement, a little bit of a thing. You can say, oh, by the way, scale our texture coordinates by 2 and 2, and well, we just want to take the RGB data from the texture and map it onto identity, so don't modify it. And then you've got an additional layer. For example, this is a separate brick layer that is being overlaid also with an RGB identity. And then you can, for example, take the light map and use a different blend function to get the plain texture as plain texture and add a colorful light map color on top of it. This is basically the typical behavior you know from Quake 3, that you get walls with flat textures and then your colorful lights on top of it, which give it the typical Quake 3 look. Well, of course, you can say different things here. You can specify how the texture is supposed to be warped, and you can overlay decals and all these kind of things. So this is, as you can see, not exactly a programming language. This is just a metadata from art specifying which texture goes where. And then there's this sort key. Back at that time, basically, if you wanted to render 3D objects, you can't really be sure that the hardware you're rendering with has any good Z buffer. I guess that buffer depth of 8 bits were normal at that time. You had Z fighting all the time. So you still had to care about how to order your things in order not to have intersecting problems. But in idTech 3, the surfaces are neither back to front nor front to back ordered, but the surfaces have a so-called sort key. All the things that are being drawn are first collected into bins according to the sort key. Then these things are drawn in order. For example, starting with the flat opaque walls, then going over the first decal layer, the second decal layer, a little bit of glow on that, and so on. And within each of these sorting tags, data is just drawn in the order that's contained into the original PK3 file. And this is important to know if we don't just want to render stuff so that it looks good, but we want to render stuff so that it looks identical to ID3. So we don't just want to get away with rendering bugs, we want to reproduce rendering bugs. Some special examples for the use of the sort key, for example, is the sky dome, which is basically just a dome whose visibility test is performed on the CPU, just vertex clipped against the boundary space, the binary space partitioning tree, and normal frustum-like visible surface correction is being done, and then it's rendered first before all the rest of the level is done. So you look at your level, see what kind of parts of the sky I might be able to see right now, render the sky first, and then render everything above it. So you don't need to test the sky against the geometry, you just render it first, and then render everything above it. But even before you do this, there are portals and mirrors. So if you have a surface that is tagged as a portal or a mirror, this is being done before the actual sky even. This portal's shape, imagine you have a door-shaped polygon. This portal shape is being done into the OpenGL the stencil buffer. It's being used to render from the view of this portal direction. Once that is drawn, then after that, the sky is being drawn around it, and then the rest of the level, which never actually overlaps this. I mean, if it actually is visible. Which means there's no memory we need to render to, no temporary textures or targets, because back in the day, these things didn't really exist in any flexible way or any way that would have looked good. So whenever you see a portal in Quake, you actually render the scene there first and then render everything around it. Which, of course, back in the time, limited the number of portals a scene could have quite effectively, because you didn't want to do 12 renders of the whole scene just to get a couple of pixels right. Okay, and then there's this volumetric fog, which, of course, as I said, the pipeline not being programmable back in the day, has to be faked in quite a neat way. There's some restrictions on what kind of fog is possible in Quake 3. It can only be axis aligned, which means you cannot have any arbitrary shape of foggy objects or any arbitrary foggy room. But you can just specify a block that is axis aligned, so rectangle which has axis aligned planes, and then a decision is made based on where the camera is. If the camera is inside the fog, then all the objects will get an additional texture layer on top of that, on top of them. First, everything is drawn as normally, and at the same time, the CPU calculates a custom texture based on your view space, which has the fog overlay for all the objects that are in there, and that is then being applied to them afterwards. And if the camera is outside, then just the fog volume itself is rendered as a flat axis-aligned plane, just like this is why the axis-aligned box is required, so that these calculations are still reasonably easy. And that is rendered as a plane above that with the also CPU-calculated fog on top of it. As you see, this is a lot different compared to how you would do these things now that you have shaders. And then there's the light grid, because levels in Quake 3 are not just like boring flat texture things, but you actually have lighting in the level affecting the lighting on the walls, and also the lighting of the actors that move through it. So it has to be a dynamical style lighting grid. So there's a voxel style 3D array with all the light directions, light diffuse color and ambient color per voxel stored. And as actors move through the scene, the voxel values will be interpolated trilinearly to the vertex positions of all actors that move around it, and then the vertex colors for these actors for the light map color will be interpolated and then processed when the thing is rendered. Okay, so that was idTech 3, and then there's Darkplaces. Since you may know Quake 3, since it's a very popular game, what is Darkplaces? You may have never heard of that, and that is another 3D engine. Here's an example of a shooter that's based on the Darkplaces engine. And you immediately see that this looks a lot more fancy than idTech 3, and you may wonder, what do they have in common? Because actually you see there's indirect lighting effects, for example, of the gun, and you can see, well, that there's YouTube encoding artifacts, but that's how it is. You can see that there's some reflecting things. You might see that there's more advanced material things than you could just do with a couple of texture layers, but you actually have specularity. You actually have, I think there's parallax mapping, although the YouTube encoding doesn't give it away. So this obviously looks like a much more modern engine. However, what it actually is a modified version of idTech1, so the very first Quake engine, developed by a guy named Lord Havoc and ported to all relevant operating systems and open sourced as well. And this originally very, very old Quake 1 engine was modified to be able to read Quake 2 and 3 files. It has been added with real-time lighting and shadow effects, all kinds of shader support, bump mapping, particle effects. So all of that has been added in to make it much more spiffy. So yeah, as you can see, explosions, blood, lightning effects, all that. And there's a couple of games like you may know Nexus and also Sonotic, which are both open source games that are based on this engine that actually look very nice nowadays. And so BRTECH1 has been built with compatibility to both idTech 3 and this Darkplaces engine in mind. And this is now where we get to the actual thing we want to talk about, that is the BRTECH1 engine, so the Bero Tech 1 engine. And here's now a video just to compare how this thing looks. Okay, so if YouTube allows us to actually display it, yeah. So this one is just a more or less random Quake 3 map that's been loaded into it, or not Quake, I think it's from, well, it's from one of the games using the Quake engine. And as you can see, first of all, it renders everything correctly and looks nice and all, but it also has more additional lighting features. You may see on the gun at the right, if you're transitioning between dark and light areas or light areas and shaded areas, that the lightning is more precise since it is no longer done per vertex, but actually done per pixel. And well, I'm not sure if shooting is going to happen, but there's a lot more visual effects that are possible in BRTECH1. You also get proper shadowing and all these kind of things. But let's go into details on the next couple of slides. So this engine has been written completely from scratch. It was not like for example, Darkplaces using the original source code of ID that has been published, but it's been engineered from a clean source code file that has been built to be able to read the data and be able to reproduce more or less, or basically exactly the visual results of these two engines and compatible with the extensions that Darkplaces has put into them. And as any or most of the projects that Bero is doing, you may know, it's written in Objects Pascal, so compatible with Delphi larger than 7 and Free Pascal larger than 2.6. And this whole effort only took maybe 2 months in July and August 2012. Yeah. So instead of this very old-fashioned style, I push polygons to the GPU rendering, it is now based on a modern rendering technique using the whole range of features that GPUs nowadays provide. So it is a deferred lighting renderer like you would expect for modern game engines. So it's basically using the old style forward renderer and then a deferred shading concept afterwards to be able to provide all the nice deferred rendering things like indirect lighting, screen space, ambient occlusion, whatever you want to do in terms of in terms of shading post-processing. And it supports multiple dynamic real-time light sources. It does soft shadows, it does all kinds of dirty tricks, and can fake area lights and all these kind of things. So how is it done nowadays? Since back in the day, you took one triangle, you gave it to the GPU, you took the next triangle, you gave it to the GPU. This is obviously no longer how you best talk to GPUs nowadays. There's actually two different ways this can be dealt with, and depending on what kind of GPUs in the system it selects between them. One is that one big vertex buffer object on the GPU is being created for each sub-area of the level. So the binary space partitioning tree basically divides the level into subsections that may or may not be rendered individually. And also within each binary space partition area, there's one of these VBOs for each material that's being rendered. So all the vertices that are being used with a certain material fall within one vertex buffer object, and there they are. And the thing about this level, this zones within levels, is that there had been a very cheap optimization put into idTech 3 at the start. Then it would be very complicated to determine what parts of the level are visible right now and which aren't. You can have a portal between, or not a portal, maybe a door between different areas of a level. At the beginning, this door is closed. You know the camera can't see the other part of the level, so it won't be rendered. But as soon as the door opens, this flag is being flipped, and from then on, the part of the level will be rendered, which is a very nice and cheap way of optimizing that only the parts where you actually walk around in will be visible in the game. Of course, nowadays, if you just take old Quake 3 maps, the performance of a GPU would be strong enough to render all the level all the time. But back in the day, this was a necessary optimization. And since it does introduce rendering, or might introduce rendering errors, it is also being emulated correctly. And the other possibility is, since not all GPUs can deal effectively with these huge VBOs containing all the data for each of the materials, there can also be one VBO for each of the binary space partitioning tree leaves and materials and all the normal frustum tests and visibility tests being applied. So that's a little bit older for better for older GPUs. Then there's things like, so there's deformations. As I mentioned earlier, you can have deformations in terms of waves, and there's the special deform autosprite and deform autosprite 2, which are objects which you would nowadays call billboards. So these are quads, for example, that are always turning to the camera, used for rendering sprites like power-up icons or these kind of things. And these are, back in the day, these were, of course, quads whose vertices were modified on the CPU and turned towards the camera all the time. And nowadays, this is done in a vertex shader, so it doesn't actually ever leave the GPU, but it's turning to face the camera all the time. For this reason, they get a special attribute for its vertex, which points to the middle of the object. So when the camera moves around it, the vertex can be processed in a way that it always turns around the middle of the object and always faces the camera. Yeah, and this is being implemented also, again, very carefully so that it matches the behavior of the original deform code in the idTech 3 engine. Okay, so here's a nice example to see how many lights it now supports, given that the original Quake engine only supported this, well, this rough light map without really independent moving lights. Here's a small test map with a moving object and some light sources moving around. You can see that the engine has no problems. These are, I think, 5 of them at the same time, or even more. Well, the engine can actually handle as many as you want. This example shows well, I think 5 of them. And you can see that shadow maps are being done correctly for all of them, and that the light interaction just works as you would expect in a modern engine and not limited by old rendering concepts. So now what's different from the original idTech 3? Of course, we are now living in the 21st century. We have flying cars and shaders in our GPUs. So it uses no fixed pipeline OpenGL anymore. It's completely GLSL based. As I said earlier, the vertex data is uploaded to the GPU once at the beginning, loading the level, and then there's no more vertex data going over the bus. So all that's being done is in the GPU, including the sprite handling and all that. So you just issue draw commands and your GPU takes care of everything looking like it's supposed to be. And of course, that means that all the typical species of shaders are being implemented here. And here's another nice example of how this may look. Yeah, you'll also see in this example that some shader-based features that are being used, for example, to display wireframes. Oh yeah, right. This is an example map that's not from the original Quake ones, but from this open source Xonotic game. Is it low? Ah, yeah, it is. Well, I don't know. I guess more people are coming to the party place now when the internet's slowing down. This one, since the Xonotic game was originally Dark Places based, it already had quite a lot of improved lighting information. So you can see here in some of the materials, I'm not sure if the outside ones have it, that there's, this is an example of the wireframe rendering, we'll talk about that later, that there's materials with specularity. Here you can see that there's actually some metal surface, so some lighting that's not just trivial Phong-based, and you can see that these ones actually have some parallax mapping on them, and emission coming from the surface itself. So these are more advanced examples, okay? Yeah, so since nowadays we have actual shaders, and back in the day we had these shader scripts, they have to be converted into each other. We don't want to do this every frame, but there's a translation engine between the original shader script into GLSL shaders. Since these original shader scripts are being loaded with the level, and there may be quite a lot of them, it's actually useful to have a shader cache so that it doesn't need to do this translation and the shader compilation for the, I don't know, hundreds of material descriptions that were in the original level every time. So it's has this the cache, so it speeds up the loading of levels enormously. And you can also then modify the GLSL code that's created and do any kind of modern lighting effect that you'd expect from a modern deferred shading engine based on your original BSP files. Okay, shadows, we've seen this in the example earlier already. They're not just like in the old Quake where you had only static objects casting proper shadows, but it's done with the shadow maps. So they are each grouped, the caster objects, basically the light sources, are grouped into render groups and sorted by viewer depth. So the typical way you are doing cascaded shadow maps by depth testing these individual shadow maps. And additionally, these can then be screen space blurred in order to provide, to provide soft shadows and not just the sharp ones. This is the typical PCSS-like blocker search data structure that you use to, in screen space, fake soft shadows. And the other thing the video earlier showed was this wireframe rendering. Back in the day in Quake 1, you just rendered your wireframe in white color, for example. Nowadays, if all of that is based on shaders, it actually, you may know how that is. If you have a shader giving you a nice material surface, and then you switch on wireframe rendering, you don't actually see much anymore because the lines in today's resolutions are very thin, and you don't actually may not want your actual material to determine your line color, since that may be black. So there's an additional GLSL shader that just takes the barycentric coordinates of each of the pixels and makes the borders of it. So basically, you have the barycentric coordinates going from one corner to the opposite edge, and just the last part of each of these areas is being, for example, drawn in white to give you the color, the white wireframes you've seen earlier. Yeah, and the 3D lightning model, since originally this was done in a voxel structure, voxel-like structure that was then used to modify the per vertex lighting information. Nowadays it's also being done in a 3D texture, or actually in two 3D texture height halves, one giving the ambient color and light direction, and one giving the diffuse color and light direction. And this information is then available, since we're now in the 21st century, to the pixel shaders. So nowadays it can be done per pixel, and it can give, well, all kinds of nice lighting effects once you have these two separate lighting information values. And this is a nice example demonstrating that. So I think this is again the Xonotic, oh no, this is actually a Quake Live map. which has the some very localized light sources. Yeah, so you see in this level you have all these spotlight sources on the ceilings where the lighting is actually very variable between areas. And as you walk around, you can see here on the gun that the lighting is being updated as you walk under them, and you can see the specular reflections on the gun and all that, reflecting that correctly. Also on the actor running around here. So this is nowadays not just done with per-vertex lighting anymore, but the modern way. And you also see some material effects on the floor if the YouTube artifacts allow that. Okay. Yeah, portals and mirrors. Now, since we don't need to do this culling and early rendering of the our portal view spaces in sort order anymore, we just leave this thing to be done with frame buffer objects and render to texture passes. Since nowadays we do have render to texture passes, and we do have them with sufficient resolution and accuracy that it actually works without any distortions or pixelization. So these will be rendered with their own viewing setup into textures, and then the portal polygon or the portal structure that shows them will then be using these as surface textures, which since it's done very carefully actually represents the old result of rendering them in early order correctly. Yes, and fog, of course, nowadays, many of you, I guess, may know how shaders work nowadays, so there's no need to do the CPU pre-calculation of a texture anymore, but actually this is now done per pixel in the pixel shader. And again, the pixel shader has been engineered in a way that it looks exactly the same as the old CPU-based fog. Unless, of course, you want to have it in a more fancy way, then you can do that with your own shader. And nowadays, what we also have is good Z buffers and good Z testing without much fighting anymore. So instead of having to draw this guy first, we can nowadays actually draw it at the last pass, which also allows us to reduce the fill rate we use up by only rendering the places where we actually need it. So there's a material tag that you can add in a shader called sky mark draw mask faces, which are the kinds of the faces in the map where actually the sky is visible. So if you have a room with an open ceiling, you would tag the ceiling as sky mark draw mask faces. And then this is the area where the sky is visible through. So these are being drawn into a stencil buffer, and only then is, based on this stencil buffer, the sky rendered above you, or wherever you may see the sky. I mean, you know some of the Quake maps that actually have sky in more than just the up direction. So the advantage of this is, by not having the sky drawn first, then everything above it, that there's no cracks and micro polygon holes on the opaque surfaces anymore. In the olden days, since resolution and maybe calculation of the transformations was a bit of a problem, there may have been some seams and cracks where the sky is shown through. This is now no longer the case. Yeah, and apart from being a nice 3D rendering engine, the BRTECH1 engine also contains an audio subsystem that does do 3D positional audio using a headroom transfer function. It does stereo rendering, it does Doppler effect, and can do underwater simulation, and is based on Bero's extensive experience with writing soft synthesizers for all kinds of sizes of demos. So you don't just get the visual, but also pretty good audio representation of your 3D scene. So how much time we got? A little bit. We still got a little bit of time, so I guess we can show this thing in action now. So this is now an example of one of the most famous Quake 3 deathmatch maps. A rather small one, I think. As you can see, most of the time, of course, now is being spent compiling shaders, I guess. And since this is just a Quake 3 map without any fancy tagging of features, you don't get any awesome lightning effects, because this is just a very basic Quake 3 map with textures everywhere. You can see on the ground, for example, the added roughness to well, added on top of the textures, and you can see that it basically looks like it's supposed to look. And here you can see the portals that are nowadays being done in a more modern way, and you can just walk right through them without, well, the game engine teleports you then instead of letting you move through slowly, but that's just the way it is. Yeah. And you can see the sky out behind you, and up there, of course, as well. So, yeah, this looks exactly like Quake 3. You wanna show one of the zoonotic maps as well for the more advanced things? Yeah, so here is a nice example of this axis-aligned fog layer, which basically just covers the ground here. And, well, back in the day, it was a hell of a cheat to do this, and nowadays it's done in the shaders, and it still looks the same. Yeah, so this is now the base Q3X, so the zoonotic version of the same thing. Yeah, and this is what the video showed earlier as well. Hoping that the Intel card in this notebook is now powerful enough to do all the shaders, because it's this is a map where basically all the features are being punched into the shader and the shader parts, doing the relief mapping and all these things. I think the shader compiler is suffering a little bit there. At least it doesn't seem to show any errors yet. Well, I don't know. I guess since we are mostly at the end of the time, maybe we go back to the slides and show the last one. Ah, here we go. Yeah. So, well, you see the GPU does it. It's not exactly fluid anymore, but it still works. And you can see on the ground here, for example, there's parallax mapping between the ground tiles. So if you move around a little bit, and you can see all the fancy materials on the metallic surfaces, where the doors had some metallic surfaces, right? You can see it maybe on the handrails here that they have nice highlight mapping, and you can, yeah, this is the wireframes we talked about. And where were these nice metallic doors? Ah, here is one of the metallic doors that has, yeah, fancy modern lighting and all that. Yeah, so the entire range from the original Quake 3 thing to this very fancy rendering is possible. And, well, I guess you are free to use it to whatever ends you want. And this basically brings us to the last slide. Oh, there's one more thing, is it? Oh, yeah, right. One map from the game World of Padman, which is a game developed in, I'm not sure exactly, some South American country. Oh, Germany, was it? But well, I think I read something on the website. But anyway, it's a very nice game that in that it has a very different visual style from most of the other idTech 3 game engine games. So yeah, this is not your average shooter, as you may see by the screenshot already, or this image already, because it basically plays inside a home or in different rooms, and also the garden of a home. And yeah, it's quite ridiculous what these developers have done with the engine. Again, the Intel card is suffering a little bit with the shaders, but I guess it's got to pull through this time. Here we go. Yeah, so this is now the kitchen, and you're a very, very tiny actor running around. And it's also got the material effects you can see on, for example, the metal. Some of these things may look like Quake, because I think some assets have been reused, but yeah, the style is very peculiar, and this also is based on the idTech 3 engine, and BRTECH1 can of course use the same. You see, oranges are jump pads, by the way, just like in real life. Yeah, you can also see there's some bloom post-processing going on, and well, there's a skybox of a city, which actually is not real geometry, but yeah, these kind of things. So, right, going to there's one more slide, I think. The one after that, I mean, the additional one. Because that is the important part you may be wondering about. If you want to use this for GPL stuff, you can use the GPL variant, and if you want to use it for commercial stuff, that is also possible, and you should just talk to Bero about it, because if you want to use it for games or you want to use it for commercial things, that is possible, as long as you are willing to use Object Pascal or Plain Pascal. All right, so I guess this concludes our demonstration of the engine, and we will take questions now. Well, I guess we've been very thorough. Then, I guess, thank you for attending in this very early morning hour, and enjoy the rest of the party, and see you around.